Thank you all for coming. I'm glad we could arrange this glimpse of the aviation revolution. And I'm going to address just aircraft, not the important evolution of airports, route architectures, business models, or sustainable aviation fuel, SAF, which dominates short-term aviation climate solutions. So here's tonight's story. Not long ago, electric vehicles, EVs, were widely thought impractical in uh, payload and range and cost because batteries were considered inherently too weak and heavy and expensive. But then smartphones spawned advanced batteries. Their higher energy density made EVs feasible. Mass production made the batteries tenfold cheaper and EVs affordable. Also importantly, lighter and sleeker cars could drive farther on less energy, needing fewer batteries and saving more weight and more cost. Ranges past 300 miles, 500, 740. More efficient EVs with better batteries won on life cycle cost, and many now cost no more to buy or even less to buy than equivalent gasoline cars. Over 60 million of the EVs once thought impossible are now on the road, with 85 million forecast for the end of this year. They are taking over the world market, and some even more advanced EVs, as you'll see later, need so little energy that they can run largely or wholly on their own solar cells without plugging in. Wow. Now this automotive history is repeating itself in aviation. The same forces that created EVs are enabling game-changing electric planes. We'll call them EPs. The EV and EP industries co-evolve swiftly with shared technologies, innovators, and supply chains. But EPs evolve faster because electric aviation enjoys virtually unlimited capital, Silicon Valley speed, not Detroit speed, vibrant competition, and higher ambition. That's good because it's harder. So I'll explain why EP's emerging evolutionary pattern will at least closely rhyme with that of EVs. That's contrary to the widely held view that aviation will use ever more fuel while road, sea, and rail transport use less fuel. In the second of these Bloomberg graphs from the left, oil-based aviation fuel in magenta keeps growing rapidly while the others go down. By 2050, it's only 7% displaced by bio-based sustainable aviation fuel in gold. But this projection assumes that aviation fleet efficiency will rise only 8% by 2050. That's a lot slower than historically. Let's see how to falsify that assumption and make the aviation graph look like the other three. I'm originally a recovering physicist, but for the past half-century, I've been a practitioner designing super-efficient vehicles, buildings, factories, and equipment. Each winter and spring quarter, Joel Swisher and I teach that experiential course Holmes mentioned on how integrative design can make the energy efficiency resource several-fold bigger, but at much lower cost than normally assumed, and often with increasing returns. So the more you save, the cheaper it gets. And that's because, as this paper shows, we use not more or fancier widgets, but fewer and simpler widgets, more artfully chosen, combined, timed, and sequenced. So we design a lot of stuff out. In 70-odd years and many millions of miles as an airline passenger, I've observed that airframe makers, although they are very good at what they do, could get much better at integrative design. What's their challenge? How far do airplanes need to fly, for example? Well, a 12,000-kilometer flight like Sydney to San Francisco is in the rightmost bar of BNEF, Bloomberg New Energy Finance's distance histogram here. But such long routes are very exceptional. Of the global aviation carbon emissions in 2023, over half came from short trips on narrow-body or smaller planes. That's the dominant four aqua bars on the left side of the graph. Just a 2,000-kilometer range could cover two-thirds of the routes. Indeed, over a sixth of the emissions come from 1,000-kilometer or shorter routes. That's a big entry market to grow volumes, improve technologies, and cut costs. We have seen this before. When Tesla introduced the first lithium-ion battery car in 2009, About 80% of U.S. car trips were under 20 kilometers, 96% were under 100 kilometers. The two-seat Roadster adopted electric drive in a lightweight Lotus Elise fiberglass and aluminum sports car, and that combination had an impressive range, 393 kilometers. And that made range a non-issue according to Car Driver magazine, but many customers still did worry about it, and there weren't any fast charging networks. The 53 kilowatt-hour battery pack was also expensive. The powertrain was handmade, so the real sticker price was 4 times that of a modern 4-seat Model 3. While providing ample range to win the confidence of early adopters, Tesla did need time to build production volume and cut costs and reduce the car's energy use per kilogram by 16%, raise its top range by 40% so you could do long road trips, and store 42% more energy per battery kilogram. The dominance of short trips bought them that time, so here we are. And now electric planes can apply the same strategy by starting with abundant short-haul markets and building out from there. However, unlike autos, planes need lift to stay airborne. Most aviation experts assert that for electric flight to get off the ground, if it ever can, it will need battery packs to store 2 or 3 times more electricity per kilogram than the best battery packs in today's EVs, and yet stay safe and durable and cheap. That is not easy. It's authoritatively forecast anyhow, but it comes from asking and answering the wrong question. That is, it simplistically compares battery versus fuel energy density and propulsive efficiency in today's aircraft, rather than redesigning the whole aircraft for electric propulsion. It's a classic case of optimizing isolated components and thereby pessimizing the system. But integrative whole system design of far more efficient airplanes can make the battery needs much milder. This was explained a decade ago in a remarkable technical paper by 2 distinguished NASA Langley aeronautical engineers. As the highlighted parts of their abstract say, the authors strongly validated my long-standing impression that electric aviation propulsion, whether from batteries or fuel cells, has compelling differences that they said will fundamentally alter the way propulsion integration is approached. Integrative design lets electric propulsion, they said, not only compete but far exceed existing propulsion solutions in many ways at battery-specific energy densities of only 400 watt-hours per pack kilogram. And that would yield, they said, 4 to 8-fold improvements in energy costs with dramatically lower total operating costs, while dramatically improving efficiency, community noise propulsion system reliability, and safety, and with zero greenhouse gas emissions if powered by carbon-free electricity, which today is 41% of world electric generation and rising quickly. So a decade ago, these NASA authors showed that, they said, for several initial applications, battery energy density was already sufficient for competitive products in some entry markets, and for many additional markets, energy densities will likely be adequate within the next 7 years for vibrant introduction. So that was 10 years ago plus 7. As we'll see, that foresight proved accurate, if not conservative. As with the solutions EV makers found, only oil enthusiasts don't yet see this coming for EPs, and hope you won't either. Now, that NASA paper shows that electric propulsion is not just another way to produce thrust, but it creates important advantages and degrees of freedom not previously available, profoundly changing how the whole aircraft is designed. Creating propulsion systems in isolation is common, but wrong. The economics are also far better for electric propulsion, changing market realities. This business opportunity, as we'll see, is here and now, and thinking it's far away risks grave disruption. While batteries' energy density is important, it is, as we'll see, already adequate if it is offset by whole aircraft improvements. Batteries do cost more and weigh more. They don't get lighter as they're drawn down. They need meticulous safety and certification. However, electric propulsion has many offsetting advantages. It has a many-fold lighter powertrain and higher efficiency than fuels do, over a huge range of scale that invites exciting distributed architectures, many small electric motors, not a few giant gas turbines. Efficiency stays high over most of the power range. Torque rises. Thrust is widely variable without gears. Energy for climbing can be recovered on descent. No combustion means no intake air or exhaust. Reliability and safety improve through greater redundancy, radical simplicity, and major power surge capability. Noise and engine dependence on density altitude nearly vanish. Higher altitude becomes feasible. Maintenance shrinks, emissions disappear. Energy costs, that is, price times usage, fall by an order of magnitude. Capital costs also shrink even at low production volumes, and then quickly fall further as volumes build. Aerodynamics can fundamentally improve. So these and other advantages are at least as big as the drawbacks. And that's how you can make electric airplanes better, safer, and cheaper than fueled airplanes. Now, bypassing the many technical details of that NASA paper, I want to offer you some simple examples and analogies to help you understand and perhaps extend those authors' compelling logic. And while I will address mainly energy efficiency, economics merit equal depth and emphasis, because economics determine what markets actually do, and in aviation, saved operating cost outweighs any extra capital cost. As Kyle Clark said in a wonderful interview with David Roberts in his Volts podcast, 19 June last year, electricity is about as much cheaper than fuel as batteries are heavier than fuel. And once you buy a battery electric aircraft, you can probably upgrade its batteries to double its range and quadruple its served cities in each decade thereafter. So it adds ever more value, unlike fueled airplanes, which steadily deteriorate from day one of operation throughout their lives. Now, here's our one equation for this evening. The fuel efficiency of airplanes is proportional to three things. Engine efficiency, that's the reciprocal of fuel use per unit thrust. Aerodynamic efficiency, the ratio of lift to drag. And a logarithmic term based on the ratio of fuel weight to gross weight, that is, structure plus payload. That third term is necessary because the plane gets lighter as it burns the fossil fuel, turning it into about 6 or 8% of climate change. So putting aside that fuel burn and some other complexities, the three prime variables to focus on are propulsive efficiency, aerodynamic efficiency, and mass efficiency, or in short, thrust, sleekness, and lightness. However, these three all interact, sometimes favorably, often not. Their interactions are complex, needing full system studies. Therefore, the many technology design opportunities I will mention and illustrate do not simply combine in a real aircraft at the systems level, nor across a full mission profile, not just cruise, but takeoff and landing and maneuver and such. So keeping that caution in mind, now back to the story. Planes go about 10 times faster than cars, and aerodynamic drag rises as the cube of speed. Well, that's really important, but reducing weight is crucial too. That's the stuff you have to hold up in the air. But of course, the numbers differ for planes and cars. However, ultralight weight plus low drag crucially enables non-fossil fueled propulsion of both kinds of vehicles. So let's spend a little time on some automotive facts, and I'll start with a physics analogy. Just a fifth of the modern electric car's fuel energy reaches the wheels and moves the car. Of that tractive load, the energy needed to move the car, nearly half, rising as the cube of speed, heats the air that the car pushes aside. Most of the rest heats the tires and road, and only the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But 19/20ths of the mass you're accelerating is the heavy steel car. So just a 20th of that 6%, or about 0.35% of the fuel energy ultimately moves the driver. Also, both acceleration and rolling resistance depend on mass, which therefore causes most of the tractive load, about 2/3. Automakers cut losses mainly in the powertrain, the red part, because that's where the big losses are. That's harder than reducing tractive load, and it's a lot less rewarding because saving a unit of fuel in the powertrain saves only 1 unit of fuel in the tank. But saving 1 unit of energy at the wheels avoids 3 or 4 additional units lost in getting the energy to the wheels, and therefore leverages 4 or 5 units of fuel saved at the tank. Well, then we can double or triple efficiency in a fueled car without changing how it's propelled. Or we can roughly quadruple to octuple efficiency by combining low tractive load with electrification. The Utility Industry's Electric Power Research Institute in Palo Alto found last year that making EVs more efficient before they're electrified can cut U.S. costs of electricity, grid, and recharging infrastructure by more than $200 billion a year by 2050. So we should therefore first reduce tractive load, then improve the powertrain, and the powertrain then shrinks for the same acceleration, F equals ma, and that saves more mass, and it also saves capital costs to help pay for the lightweighting. So how can that lovely synergy work in practice? Well, let's look at this carbon fiber car that I drive. It's 55 kilograms lighter than a two-seat, this is half as many seats, 2009 Tesla Roadster. And it was profitable from the first unit that BMW sold in 2013, and for all 250,000 units sold over the next 9 years. But it's made of carbon fiber, which automakers had rejected as far too costly. Well, the trick is the carbon fiber was paid for by needing fewer batteries to propel the lighter weight car, and then fewer batteries recharge faster, they need less electricity and infrastructure, and therefore less money. Saved weight, about 300 kilograms, snowballs spectacularly, saving about 1.5 to 2.5 kilograms of secondary weight for each kilogram of saved primary weight. The assembly saves 2/3 of the normal capital and water and half the normal energy, space, and time. It eliminates the 2 hardest steps in automaking. It's much better for the workers, and it ends up quadrupling efficiency without compromise and with many driver advantages, of which my favorite is half normal turn radius and terrific visibility, no blind spot. This design logic could also save up to 2/3 of the scarce battery minerals, and then there are 5 other multiplicative forms of efficiency to manage the rest. Well, BMW finished producing this model in mid-2022, although there are calls to resume production, and I suggested if they don't do that, they should just give the tooling to Ukraine. Meanwhile, Bloomberg says China's strategy for its 2030 flagship cars includes carbon fiber structures displacing 4/5 of their iron and steel. And if that happens, it could flip the global car industry. China already makes impressive EVs, some priced at just $5,000 to $10,000. So if China designed out another half to 2/3 of the costliest ingredient of its EVs, automakers elsewhere would have to follow suit or lose share. Now, lightweighting is especially important because of mass decompounding, the snowballing of saved weight achieved by going repeatedly around the design spiral or design cycle. So starting at the left, first you make the vehicle light and slippery, so you cut its tractive load, say, in half, and enable smaller and more advanced powertrain and smaller, lighter chassis components, less suspension to hold it up, less brake to stop it, and so on. Those leave more packaging volume and more crush space for safety. Then you go around the spiral again, making components smaller as the structural loads shrink, because the less weight you have, the less weight you need. Lightness multiplies. But such recursions can also eliminate components. So pretty soon you probably get to a good series hybrid that does not need, transmission, clutch, flywheel, drive shaft, U-joints, axles, differentials, starter, alternator. That's 9 things that go away, and each elimination of a thing triggers another cycle of mass decompounding as you go around the loop some more. At first, the special materials and powertrain and design might seem too costly, as in the lower part of the graph, but after a lot of recursive cycles of mass decompounding, you need so little carbon fiber and such a small powertrain that with the simplified manufacturing, the total cost can revert to normal or even less. Of course, that's cost per car, the way you buy a car. It is not cost per part or per kilogram, which is how most automakers and even the national academies mistakenly think about cost. Aerospace designers are much more sophisticated than automakers about saving weight, but often not yet enough, and not only about weight. I once asked a room full of the top designers at a top airframe maker, what is it worth, whole system, end-to-end life cycle cost of ownership, to take a watt of electric load out of your airplane? Half of them didn't know the number, but they were sure someone else in the company did. The other half scratched their heads a bit and said, well, actually, nobody in the company knows that number because we never asked that question before. It's an important question. It's complicated. We'd better figure it out. Well, I hope they do. Now, strong lightweighting takes radical simplification. Let me tell you a story. Tesla's original Roadster had a two-speed gearbox that kept blowing up because it couldn't deliver 0 to 60 miles an hour in 4.6 seconds and 125 mile an hour top speed. After two manufacturers failed, the chief engineer, J.B. Straubel, was griping one day. I said, gee, I suspect the right answer is probably no gearbox, just a single-speed reduction gear. So he thought about that, and one day he came in and told his team, let's insource this problem to our core capability. We are electrical engineers. If our motor produces a third more torque, we won't need the gearbox, and then we'll tweak the power electronics and software to match. They protested, but the motor will overheat. You'll have to band-aid on some Baroque cooling system. He said, oh, don't worry, we'll figure out what's getting hot and give it better conductivity or a bigger cross-section. And so was born the 2010 Roadster 1.5, which eliminated the gearbox. That gained 16 kilometers of range, saved over 6 kilos of weight, 30 kilowatts more tractive power, less noise, less maintenance, less warranty cost, and 3-digit fewer manufacturing dollars in an industry that'll kill for a nickel. That little story and its competitive implications later triggered the electrification revolution at a major U.S. automaker. The same relentless pressure for simplification is now overcoming automakers' tendency to equip components with individual heating and cooling systems, or with forests of hoses. Tesla's Model 3 instead used a single-bolted plastic heart whose four-way valve redirects thermal energy real-time from where it is to where it's needed, optimally sequencing and cascading temperatures. It took Sandy Munro 2 weeks to figure out how it worked. It was that clever. And likewise, of 5 separate power-related modules in the Chevrolet Bolt stacked together in the left photo, Tesla's Model 3 eliminates 2 and consolidates 2 more into other modules. So again, it radically simplifies the system and achieves the same familiar suite of benefits. Airplanes offer similar opportunities, they're just more valuable. Now, how low can the tractive load of cars go? Well, this table from my 2020 Society of Automotive Engineers paper, Reframing Automotive Fuel Efficiency, shows how my early 90s analysis of 6 critical platform parameters inferred from historic concept car and component data what efficiencies in the second column production cars should be able to achieve over several decades, that is, by about now, because the papers were in the early 90s. Those empirically grounded estimates were heavily criticized at the time, but 3 decades later, they are eerily close to the market offerings on the right. That kind of over-the-horizon radar signal is vital if you want to substitute accurate technological foresight for marketplace shocks. I think collecting weak but real signals can enable accurate inferences about future aviation too, because whatever exists is possible. So let me offer you a suite of further examples. Remember how saving automotive energy by taking out mass or drag leverages much bigger fuel savings back at the tank? Well, the same is true in planes, but it's even more valuable, and you have to carry the fuel around in the air. So with a 40-odd% efficient jet engine, each unit of mass or of lift to drag ratio saved in the airplane saves over 2 units of fuel directly, and then even more with mass decompounding. This multiplier also raises the value of saving onboard electricity. Even a quite efficient 787 Dreamliner drawing about 400 kilowatts of electric power at cruise is not yet fully optimized. Optimization for whole system lifecycle value might show, let's just make up an example, that if you replace this $20 coffee pot with a $200 vacuum super insulated internal element coffee pot, maybe it'll save thousands of dollars worth of fuel each year. Boeing estimated that optimizing electric loads might add a couple of percentage points to the 787's roughly 20% gain in fuel efficiency. Even more when smart wiring and power management save a lot of heavy, complex wire. But I wouldn't dream of providing thermal comfort in a building the way we do in airplanes. A lot of redesign to be done, and we still have a long way to go with some fundamentals like taking out weight, even operational weight that is not built into structures. You see, taking a kilogram of weight out of a typical commercial airplane is worth about $2,000 in present valued fuel cost. Even more on long flights where each liter you want to land with requires another half to 1 liter to carry the first liter across the Pacific. I was once hitchhiking on a KC-135R military tanker, and I noticed a whole bunch of heavy objects that didn't need to be there. So next morning, I briefed my observation to a couple of Air Force 2-stars, and that afternoon they launched a treasure hunt, and they found in that class of airplane $2 billion worth of weight savings and fuel savings that nobody had been responsible or rewarded for taking out. Likewise, as an airline passenger, I noticed very uneven attention to weight. They really sweat the details of lightweight toilet paper and magazines while overlooking very heavy tray tables and, until very recently, heavy galley carts. And, of course, airframe makers could do a lot more with basic structural weight, too. Our lightest big passenger planes are still only half carbon fiber composites by mass, but 3 decades ago, Dave Taggart at the Lockheed Martin Skunk Works led for DARPA the design of a 95% carbon composites advanced tactical fighter airframe that was 1/3 lighter but 2/3 cheaper than the 72% metal base design for this joint air strike technology, later called the Joint Strike Fighter. Here's a closer and flatter look at it. Here are some of the benchmark numbers. The 3 or 4-fold lower production cost for this 735 kilogram lighter airframe showed, as BMW did for cars later, that ultralighting need not cost more and may cost less. And the cost would be even lower today because the leader of this Skunk Works project moved to RMI in 2000 and led our hypercar spin-off's development of a cost-effective SUV with half the normal weight and 4 to 6 times greater efficiency, but a U.S. retail payback under 2 years at mid-volume. A team led by another RMI engineer at that spin-off, now head of advanced composites at Apple, where BMW's iProject leader then led the Titan car project, later developed the fiber forge process that makes competitive structural carbon fiber parts, and it made this test piece, my carbon cap, for military ballistic helmets in 1 minute 16 years ago. It's tougher than titanium, rings like a bell. I'll pass this stuff around, just please make sure I get it back. And this process then made a lot of airplane parts like composite window frames that went from concept to commercial flight in 6 months. We sold the technology to a German Tier 1 pressmaker in 2013, and the process as embodied in this machine released 3 years later can make a complex 2 by 2 meter structural carbon fiber part in 1 minute, or over 1 million smaller aerospace parts per year. It can become several-fold faster if desired. Here's another couple of bits. That's a piece of helicopter floor that is marine-proof. That is, a Marine with a fire axe can't do any damage to it. And probably not used to having plastic sound like that. But This machine could also become several-fold faster if desired. I mentioned this technology just in case any of you think that making advanced composite airplanes and their structural components has to be small and costly. It doesn't. Now, to be sure, advanced composites are slowly and incrementally displacing metal one piece at a time. Current trends include carbon fiber wings and elliptical fuselage forms that have a 787-like passenger compartment on top of a skinnier 737-like cargo hold, so you can fit more seats with less drag and less weight. But a lot of components still made of metal in airplanes should not be, and the barriers are not mainly technical or economic, they're cultural. Radical designs like that 95% carbon composite joint strike fighter require revolutionary design mentality, designing in the future, not in the past. When the Soviets shot down Francis Gary Powers' U-2 spy plane in 1960, Kelly Johnson, head of the Skunk Works, did not say, "I'm going to design a slightly better U-2. He said, in paraphrase, "I want to own the skies for decades, so we'll design a Blackbird, SR-71. I don't know how, but we'll figure out." They did. It took about 13 months. Because Johnson understood that such an airplane was impossible within the conventional design context. That's because design is like a rubber band. If you try to stretch it too far from the conventional design space, you encounter more and more resistance and eventually it breaks. But if you jump to the new design space you aspire to, you can stretch the rubber band back to fit technologies that aren't ripe yet, and then as they mature, the rubber band relaxes to where you wanted to end up. Ultralighting requires also not just smart and uninhibited designers and thinking in designing in the future, it also requires organizing the designers differently. Dave Taggart brought us from the Skunk Works our Revolution SUV's design process. We had 7 engineers all around the same table, collectively responsible for dauntingly ambitious whole vehicle requirements that the industry had no idea how to meet. Each engineer also owned one major vehicle system or function, but for those we deliberately wrote no requirements because we didn't want him to make his problem into her problem. We wanted to make the whole team design a highly integrated vehicle together. 2 of the engineers were not comfortable without their very own requirements, so in the first couple of weeks we replaced those folks, and then it went great and we got the intended result. Toyota asked how we did it. We told them, and in 2007 out came a 70% lighter, that is a 400 kilogram hybrid concept car you'll see called the 1X. And thus the ultralight carbon fiber electrified hypercars that I invented 34 years ago and we designed with industry 25 years ago developed those design methods that Toyota used 18 years ago to design that 70% lighter 1X hybrid. Similar methods then entered the market in 2013 with the popular and profitable BMW i3 I showed you earlier. But even 1-ton lighter aluminum fleet vans like this hybrid that another RMI spinoff developed and road tested in 2009 could save 1/5 of U.S. auto fuel at lower life cycle cost with no subsidy. And carbon fiber autos made in our simplified way at normal cost could save more oil than Saudi Arabia lifts at an extra cost that a decade ago was under $18 per saved barrel. Today it's in the $0 to $7 range. And indeed, 2/3 of the EVs now made in China are already at or below sticker price parity with their gasoline equivalents. In other words, they save oil at negative capital cost, and so do 2 popular U.S. electric vehicles. Well, now aeronautical structures could be made in radically different ways that Kelly Johnson would have been all over. 6 years ago, MIT's Center for Bits and Atoms introduced a flexible lattice structure illustrated by this 4.3 meter test structure that is 59 times less dense than a typical metal aircraft wing. That's 59 times, not 59%. Such a structure has the strength of the bulk elastomers, but the gossamer density of aerogel. It can also eliminate movable flight surfaces. Every part of its entire shape passively adapts to optimize continuously for real-time flight conditions like a bird's wing. Thousands of such identical anisotropic molded polymer little cells of centimeter dimensions can be assembled by swarms of programmed robots or grad students, whichever are cheaper, into an airplane of any desired shape. And this cutting-edge technique opens revolutionary prospects for lightweighting, aerodynamics, and cost reduction. It has been prototyped as an airplane for Airbus and as a car for Toyota. It can even form a vacuum balloon, buoyant but crush-proof in air, and a really big one could lift 24 times the payload of a 747. Alternatively, these hooked-together miniature structures are as strong and stiff as solid structures, but they're up to 90% air. They don't even use carbon fiber. After carbon fiber could come Miralon's or Dexmat's carbon nanotube structures with up to 10 times higher mechanical performance. And now we can make similar near nanotubes from sugar, water, and sunlight via the bacterial enzymes that hummingbirds use to weave their nests. Another approach uses nanoprinted metals with optimized microstructures. Airbus's collaboration with Autodesk generated this 45% lighter partition for the A320 and exciting design concepts for whole airplanes. Of course, the same logic applies to 3D printed metal parts as to bird bones. As usual, nature has done all this before. Indeed, extinct pterosaurs, the biggest flying creatures in the history of life on Earth, had wingspans of about 10 or 11 meters, 3 times that of today's biggest birds, thanks to bones with paper-thin walls stiffened by internal struts. There's a new Nature paper revealing complex porosities that made the bones much lighter, slightly bendier, and able to combat and heal cracks. So this paleobiomimicry is applying designs from 1/6 of a billion years ago to improve today's aerospace structures. Way cool. Of course, airplanes have long been getting more efficient. Those U.S. certified from 1960 to 2000 cut fuel intensity by 70%, half from better airframes, half from better engines. That progress remains on such a steady and plodding course that Boeing's so-called NMA, or 797, was expected to hit this year exactly the efficiency bullseye that we had estimated in 2004. But uncertain and often cash-short customers, incremental thinking, restricted vision, market turbulence, and Boeing's recent deculturation make the industry's trajectory too slow, raising efficiency by just 20% per generation. And at that rate, it could take another century to do what we knew how to do a decade ago. By then, we're cooked. Aviation does about 6 or 8% of the cooking. Next generation options are well known and effective and profitable. Among the most obvious prospects already emerging, advanced composites will lighten aircraft by at least another 20% and enable the elliptical fuselage. Morphing wing technology can save over 10% of fuel in new clean sheet design and over 3% in retrofits while reducing noise 10 dB. Geared turbofans can be 15% more efficient than conventional jet engines. Blended wing body designs can often save over 40% if we change manufacturing and how we board and deplane. But there are a lot of other innovations available, and they get powerful in combinations. In 2013, NASA did this roadmap for seeing 50% fuel savings from the 2015 baseline would be available by 2020 and 60% by this year, 2025, as shown in the right-hand yellow column. However, airframe makers moved much slower to adopt these pretty obvious techniques. These are some designs to illustrate how more ambitious combinations of current technologies can boost the U.S. commercial fleet's efficiency cost-effectively by 3 to 5-fold over its 2005 level. The upper 3 designs are from Boeing, NASA, and MIT. They're a decade old. The lower 3 are several years old. Both sets can save about 50 to 80% of the fuel versus the 2005 best-in-class or versus today's fleet. They use things like strut-braced or truss-braced wings, riblets, advanced composite structures, hybrid electric propulsion with gas turbine-assisted takeoff and range reserve, but electric cruise, podded or buried propulsors, boundary layer ingestion, some blended wing body designs, like in the bottom middle, and other expanding innovations. The then chief scientist of NASA Langley, Dennis Bushnell, told me 6 years ago that just proper application of truss-braced wings with advanced aerodynamics can raise the lift-to-drag ratio from about 18 or 19 with tube and wing designs, or about 22 or 23 with blended wing body, to 40 to 60 plus, while considerably reducing weight. The Swiss laminar flow wizard Werner Pfenninger even designed lift-to-drag as high as 100, nearly 5 times current norms. Very impressive. The best German gliders are in the 70s. Bushnell suggests further adding other refinements. For example, he suggests thrust vectoring from fully aft propulsors to eliminate the tail, the empennage, and replacing landing gear and heavy brakes, which total on the order of half the fuselage weight, with lower impact automatic landing and deployable parachutes for refused takeoffs. So there's still a lot of hidden treasure out there. Even simple changes can be highly effective. Looking out the window as an old plane lands, I've seen the flaps extended by a hydraulic and mechanical system that the wizard of electric actuators, Del Tessar in Texas, who used to be a farm boy gearhead, rightly calls farm machinery. That's exactly what it is. It is heavy, unreliable, costly to buy, costly to maintain. It does not belong on an airplane. He would replace it with a 5-fold more durable, far more reliable and repairable, and much cheaper hinge line electric actuator, and that cuts the overall system weight by a factor 3. Next, we can eliminate hinged flight surfaces. Like the Wright brothers' bendable canvas and wood, flight surfaces can now morph real-time to adapt to flight conditions, leaving the surface and airflow smooth, as in these two methods. The first method has entered the supercar market in front and rear wings for an Aston Martin. They morph to maintain downforce at any speed. It's also expected to save about 2 to 11% of the fuel in planes, and the Air Force has committed to deploy it on several hundred once flight tests are completed. The second method uses the lattice and membrane structure you just saw. Nature is rich in great aeronautic designs like the tropical cucumber seed that can glide for hundreds of meters. Not to mention the California condor. Just besides all its advanced geometries and structures and controls, I especially like fully integrated system design and advanced manufacturing techniques listed by the late great aerodynamicist Paul McCrady, who gave me this picture. Now, can biomimicry raise propulsion efficiency? Jay Harmon is an Australian naturalist and sea captain. He's imitated the Fibonacci structure in natural vortices on the left to make super efficient fan and pump motors like the tulip-shaped pump rotor on the right that can spin underwater at thousands of RPM with no cavitation. Now, if your 100,000 or so kilometers of fractal blood vessels had the design and friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But your third of a kilogram, 1.5 watt heart suffices because your bloodstream uses laminar vortex flow. Airplanes don't do that yet. They should. Disclosure, I own about 1,000th of Jay's holding company, which is called Pax Scientific. Such rotors can empirically raise pump and fan efficiency by about 20 or 30%, not quite violating the pump equation, and computed and observed pump behavior now match up nicely. Some of Pax's diverse super-efficient fans, propulsors, winglets, hulls are now on or entering the market. Remarkably, their efficiency gains are independent of scale and independent of Reynolds number. So for air as for water, cheaply converting standard fuselage airflow to laminar vortex flow or toroidal flow regimes, everting toroids going back, can cut drag. And in one early torpedo trial, they cut drag by 14%. Remember, the Reynolds number doesn't matter, so you should be able to do the same thing in air. Number may differ. Pax's household fans are far more efficient and quieter than conventional fans. The latest one at the bottom uses 50 to 85% less power per unit of flow than its competitors from Holmes, Vornado, and even Dyson, while providing higher air velocity with a lot less noise. Might its principles yield more efficient propulsors? Just a fan backwards. Safran and GE's joint venture CFM International is testing an unducted or open rotor with one rotating stage and one stage of non-rotating variable pitch blades. Bypass ratio is over 70 versus 10 for a giant 777 engine with its carbon fiber blades. A 20% fuel saving is expected in service by the mid-2030s. I wonder if such designs could benefit from subtle Fibonacci shapes like Harman's biomimetic fan blades. Another suggestive innovation, rediscovering a 120-year history with over 160 patents, is the award-winning toroidal propulsor for quiet drones on the left, developed by MIT Lincoln Lab. An old concept said in the U.S. patent to improve lift to drag by 40 to 60%. They were working on ring wings, and some 35–40% of a typical aircraft drag is due to wingtip vortex formation, but the toroidal propulsion or propulsor has no wingtips and therefore no vortices shedding off them. It may weigh more or maybe less per unit thrust, depending on the materials. There's a parallel development by a musician seeking to abate annoying drone noise, and it's been successfully commercialized as a marine propeller on the right, available 3D printed from online makers, or in this elegant marine bronze from Sharrow Marine, and both air and marine versions can reduce fuel use and acoustic signatures very markedly. Now let's start putting these pieces together. 4 years ago, I visited William Otto Sr. and his team in Southern California. Bill used to be chief scientist avionics for the B-1 bomber. He has quite a team, and since '07, his firm has been developing this radically optimized plane that exited stealth mode 5 years ago. It has demonstrated about 59% lower drag than a standard business jet, thanks to highly laminar flow, I'll call it super laminar, over the entire fuselage and wings and tail. The critical areas, most of the plane, have no rivets, no seams, no gaskets, no gaps. This initial design, called the Calera 500L, aimed at type certification this year as a $5 million business plane, which has a 6 foot 2 inch stand-up cabin height and longer range than a 737. But after 3 years of successful test flights, the firm decided to leapfrog straight to bigger models. And superlaminar flow is clearly feasible in regional jet size, and Airbus work suggests it looks possible up to about 737 size. But all sizes could blow up the business models for general aviation and carriers because smaller, cheaper planes are perfect for rapidly emerging point-to-point route architectures serving any of over 5,000 U.S. airports instead of just big hubs. Now, the initial engine for this demonstrator is a 500 horsepower twin-six aluminum diesel, turbo diesel that can burn any fuel, including pure SAF. But a diesel engine is not the only option. 3 years ago, Auto Aviation confirmed plans for a 19-seat, 1,000 nautical mile range, mid-size 2027 version powered by a ZeroAvia hydrogen fuel cell system. That powertrain has already flown in a 19-seat test bed. It's been tested in a Dash 8. Its operating economics should beat even the ultra-cheap diesel due to even lower drag, less propulsion system maintenance, and cheaper fuel. Electric designs are also underway and look very promising because the super efficiency displaces many heavy batteries. I think this may be the most important new plane family in decades. And now we're starting to hear about the transonic superlaminar Calera 800. But let me just point out that the 500 demonstrator can go, say, San Francisco to Dublin on 1/8 the normal fuel. I mentioned earlier factor 8 efficiency was already demonstrated some years ago in this state. Now, as is usual with integrative design, benefits compound. greater lift-to-drag ratio reduces the fuel volume and weight for a given range. Less fuel means smaller wings and powertrain and structures. So a 30% drag reduction compounds into about a 60% fuel saving. Moreover, sustainable aviation fuel's higher price is more than offset by saved fuel, so the direct operating costs using pure SAF can be half those of a standard business jet burning Jet A. The Calera 800 design's carbon emissions, 36 grams CO2 per seat mile, are virtually identical to those of common EVs at 34. Another fun innovation is panoramic digital windows, which they call supernatural windows, that save weight and improve laminar flow, promote thermal and visual comfort, and make the cabin 20% bigger. Back in 2011 and 12, EADS, now Airbus, published a provocative technical design study for a largely laminar flow, bulbous, pusher fan, 68-passenger turboprop, 900 nautical mile range, some basic efficiency improvements. So it had about 25% greater energy efficiency, therefore smaller batteries, and then the resulting decompoundings of mass and other burdens could reverse, they found, more than half of the near doubling of weight from the electrification. Again, showing you can do far more with milder battery progress. And the authors at EADS concluded that, they said, typical payload and range missions flown today can thus be realized with 750 watt-hour per kilogram battery systems, compared to 1,000 necessary for the conventional configuration. In other words, you can do the same thing with far less ambitious batteries if you also get very efficient. Well, that was correct in 2011. Now we can do much better. It would not surprise me if ultralighting and ultralaminar flow and other efficiency advances already proven and starting to enter the market could converge with better batteries and motors and power electronics and even ultralight photovoltaics, some already commercial at 40% efficiency, to make electric planes rival, if not surpass, the key parameters of today's kerosene planes. That is exactly what just happened with battery electric cars. Even I used to think that those were, as a Dutch critic put it, cars for carrying mainly batteries, but not very far, not very fast, or else they'd have to carry even more batteries. Well, that was wrong, and now I own two fine battery electric cars. I wouldn't dream of going back, and today's best battery electric cars beat fossil-fueled cars in every way. Let's look at a few interesting car examples. This doesn't have to depend on new materials. As our aluminum van showed 16 years ago, you can do a lot even without carbon fiber. Lucid's Air model, Newark, California, the Motor Trend Car of the Year in 22, uses a compact powertrain to help fit a spacious luxury interior into a mid-size package. And it's so efficient, it got a record EPA range rating of 512 miles and does 0 to 60 miles an hour in as little as 1.9 seconds. Can your gasoline car do that? Will your neck tolerate it? Mercedes did a developmental car in 2022, 252 miles per gallon equivalent, thanks to a 95% battery to wheels efficiency, exemplary drag coefficient of 0.17, and a lighter curb mass. And that tested at a range of 747 miles, over 1,200 kilometers, with a battery sized for a compact EV. The battery pack is 30% lighter and 50% smaller than in the comparable production model. That just shows you how fast batteries are evolving with the help of electric race car technologies. So I think range technology is going to become as obsolete as the speed of your modem. Remember modems? You might be too young to remember modems. And despite some fiberglass, this sedan is basically steel and aluminum. It's not advanced composites, so there's a good deal more range and efficiency on the table. Some of the powertrain, by the way, is in the CLA model that Mercedes is bringing to market late this year. Well, now the next efficiency leapfrog is emerging. Two solar-powered hypercars, both from little firms I advise, are ready to mass produce as soon as they finish raising their last bit of production capital. And most drivers will never need to recharge this two-seat electric vehicle because its solar cells capture enough energy to drive 40 to 60 kilometers a day. It's as if your present car magically added 2 gallons of fuel to its tank every day you park it outside. To make a long trip, you can quickly recharge the tiny batteries, as in the lower left picture, with household electricity, and they plan models with ranges up to 1,000 miles. Now, my BMW and Tesla electric cars are among the most efficient now sold, but this two-seater with a very crashworthy carbon body is going to nearly triple Tesla efficiency to the equivalent of 343 miles a gallon. Then there's the Dutch firm Lightyear, also ready to produce a 5-seat four-wheel, light, very aerodynamic car with 5 instead of 3 square meters of solar cells on top, 251 miles per gallon efficiency, and it can add about 12 kilometers of range per hour in the sun. So the charging infrastructure that conventional EVs have to pay for, these super efficient vehicles aim to bypass, and even they can be further improved. There's a similar story, by the way, in electric heavy trucks. Tesla's Semi 18-wheeler triples to sextuples current fleet efficiency with impressive economics, but critics thought its extra battery weight would reduce its payload. Turns out not to be true. The propulsion equipment is much lighter, so displacing 3 tons of diesel powertrain and its fuel keeps the payload unchanged with just modest lightweighting of the platform, and that could expand further if Tesla decides for marketing reasons to raise the standard payload. That'd be pretty neat. How about aviation propulsion? Well, in gas turbines, the National Academies expect several more decades of 7% per decade efficiency gains beyond the current, probably a bit over 55%. GE's 3D printed complex fuel nozzles famously helped make one engine 1/10 more efficient. 8 years ago, this business jet turbofan delivered 10% more power from 5% less weight with 20% less fuel and 99% fewer parts. GE has a production version called Catalyst, the first clean sheet turboprop engine in over a half-century that was just certified by FAA and has a 16-to-1 pressure ratio. Last year, GE invested over $650 million in full-scale production of 3D printing-enabled engines for bigger planes, including one with over 300 3D printed parts. That's the GE9X engine for the giant 777X planes. And GE uses ceramic matrix composites for turbine blades that have 1/3 the weight of steel, but they remain strong at over 1,300 Celsius, above the melting point of many superalloys. And yet, coming up fast in the outside lane are electric and hydrogen-powered airplanes. And the hydrogen ones sometimes use gas turbines, but usually they're fuel cells. I'll sketch some highlights of those in a moment. There are also very extensive and long-standing military investments in these technologies and others that ultimately finds its way into the civilian sector. That's not yet visible in the unclassified world or reflected in market expectations and planning forecasts, but clearly it's going to accelerate what I'll describe next. It's no accident that the maker of the most advanced always aloft solar airplanes is the same company, AeroVironment, that makes the Switchblade backpack portable drones now used in Ukraine. It also, by the way, makes my BMW's EV charger. And with drone innovation now critical to the outcome of Putin's war, and Ukraine making millions of drones a year, evolving in cycles as short as days, new techniques will reach our civilian aviation much faster. So here's a hint of coming attractions. There's an Air Force surveillance drone that's been revealed to be now operating in the Middle East. It costs nearly an order of magnitude less than a Reaper drone. It can fly a 400-pound payload for 80 hours. And at the other end of the spectrum, we now have firms like Walmart and Amazon already using drones for home delivery. It's a lot cheaper than driving a heavy truck around. Now, a critical technology for electrifying aviation is the electric motors in between the power source and the propulsor. There are some powerful EP motors that are now 2 to 10 times lighter than today's EVs use. The best aviation motors, here's a couple of examples, now deliver 25 to 28 continuous kilowatts per kilogram. That's nearly 3 times more power dense than the best EV motor from Lucid. It's about twice as good as the best e-racing motor. The example on the right, which you could stack up to a megawatt, beats the Air Force's 20-year goal by a factor 5. That's out of Oxford. Sleeker, lighter planes also need smarter motors and batteries, but those do not suffer lower efficiency as smaller gas turbines do. And top analysts now agree that EPs will generally have lower capital cost and lower operating costs than fueled planes, and that will drive rapid adoption in both commercial and private aviation. In case you worry about critical materials, many fine light motors, both induction, also known as asynchronous, and reluctance machines, have no permanent magnets. And there are 2 kinds of supermagnets that contain no rare earths. One of them is iron nitride that promises to be up to twice as strong as neodymium iron boron. That stuff's entering the market. Inverters are progressing from silicon switches to silicon carbide to nearly lossless passively cooled gallium nitride. Kilovolt silicon carbide switch ratings now make wiring small and light. And the powertrain in that Dutch Lightyear EV is 97% efficient battery to wheels, 2 points ahead of the Mercedes developmental car I showed you. The best e-racing motors and inverters each are about 99% efficient. So a lot of losses still to go away. So electric flight is becoming practical because many diverse technologies, not just better batteries, are converging in this kind of vast Cambrian explosion of innovation. EPs have scores of skilled, serious, amply funded developers, total maybe over 200 of them for bigger platforms and over 1,000 for urban air mobility vehicles. There are about 9,000 orders for types with up to 30 seats. There are at least 55 intending operators as of 5 quarters ago. When McKinsey estimated a future air mobility order book of over 21,000 aircraft, not all firm orders, worth $118 billion. And altogether, they found more electric aircraft than fueled aircraft are on order in the world. And then there are over 9,000 electric vertical takeoff and landing, or eVTOL, air taxis, millions of drones, and military R&D, all further enriching this e-aviation ecosystem. Joby's planned eVTOL taxi service around this year from downtown New York and LA to JFK, Newark, LAX airports looks on track so far. Their first delivery to the Pentagon was last year, and Joby announced today its successful testing a week ago of the challenging transition from vertical to horizontal flight and back. They've now had 3 pilots doing that routinely. That firm has raised $2 billion from such investors as Toyota, Intel, Delta Airlines. It ended last year with nearly $1 billion of cash on hand, another $500 million receivable. 2 years ago, they got FAA approval to carry passengers. Archer just did that as well, and they hope to start serving United Airlines this year. It's not hard to see the attraction. London Heathrow to Canary Wharf in 11 minutes. That's 85 to 93% faster than by car, and you're confident of getting there. And the prices should soon fall below helicopters. And around 2030, a lot of analysts think they'll match the price of an Uber premium car. And now, to be sure, the German eVTOL fanjet firm Lilium collapsed. Volocopter had to be bought by Diamond. Aviation is being restructured. But, some business failures were expected, and meanwhile, new players are emerging. The biggest uncertainty remains timely regulation. FAA fell behind setting drone certification standards, and that also slowed piloted plane certifications. Some developers stumbled. The pandemic slowed everybody down. But some e-aviation type certifications are well along, and FAA is now rising to the challenge. So happily, flights without fuel can start resolving communities' CO2 and air pollution and health concerns by eliminating emissions and turbine noise, just as in ground vehicles. Now, whether or not eVTOL air taxis become common, electrification is going to present new challenges and opportunities to airports and to carriers. To run planes of all sizes and shapes, competition between advanced biofuels, electricity, power to fuel, and hydrogen is going to turn airports into integrated transport and energy hubs, probably using distributed models and designed for resilience. But electric air taxis will almost certainly use a lot more energy than electric ground taxis. Collisions are a lot more serious in the air. There are some real security concerns like using eVTOL drones to deliver bombs. And if you like congestion in 2 dimensions, you'll love it in 3 dimensions. So this is all going to take a lot of careful foresight. But first of all, will electric planes actually take off in the market? Or are the skeptics right that they will never fly? Well, if you think EVs are pie in the sky, you might consider whether this who's who of vendors and operators of electric planes all got it wrong. I hope skeptics will carefully read Kyle Clark's Volts interview I mentioned earlier and ask themselves if they are surprised that Beta's eVTOL has flown a 600-pound payload for 386 nautical miles. Some skeptics may need to reconsider papers like one eminent aeronautical engineer's widely circulated screed called The Total Impracticality of Electric Aviation, which concludes that electric aircraft can never be more than expensive toys. Well, we'll see. How many of these firms would you like to bet against? How about all of them? Or consider these counterparts in the hydrogen plane ecosystem. Now, to be sure, Airbus just slowed its hydrogen plane program by 5 or 10 years, mainly due to slow development of airport and fuel infrastructure. But as we have seen, tenfold carbon savings offer juicy economics without hydrogen. Hydrogen also gets easier as planes get far more efficient and hydrogen production gets decentralized. So I think it's more likely that incrementally minded incumbents and commentators are deceiving themselves and likely to miss their flights. Now, I mentioned earlier battery energy density. The most advanced civilian solar airplane a decade ago was my buddy Bertrand Piccard's Solar Impulse 2, 260 watt hours per kilogram at the pack level, weighed 2,000 kilograms to take off, and it circled the globe. Well, now, 9 years later, at least 3 firms have doubled the pouch cell's energy density in smartphones to 400 or 500 watt hours per kilo. That's about 3/4 of the pack energy density that the National Academy said 9 years ago would take 20 years. Some firms are around 900, at least on the lab bench. And the lithium battery giant in China, CATL, announced 2 years ago a condensed battery with around 500 watt hours per kilo at the cell. They also mentioned a little partnership that had tested a 4-ton electric civil aircraft. In another 2 or 3 years, they say an 8-ton version with 2 or 3,000 kilometer range. Companies like that can move really fast. Now, without digging into all the technical details of the batteries, we can get back to this if you want. I just want to emphasize that battery energy density is fungible with platform efficiency. And I've been riffing back and forth between the aviation and automotive revolutions because they inform and supply and feed on each other's. Planes do go faster than cars. I think that's now true of their respective innovations. And there may be innovation drivers lurking just outside our view, as happened with lithium batteries. I think I'll skip over the hydrogen details. If you go to the ZeroAvia website, that's a partnership based in Britain with British Airways, United, Alaska Airlines, Schiphol Airport, a bunch of others, you'll find a very ambitious timeline, but it doesn't look unrealistic. And we see a lot of examples of this. Picard is now heading for around the world 9-day nonstop flight planned for 2028 using liquid hydrogen. And it's really unwise to stand with your back to a stampeding herd of technobison. Let me end with a few little illustrations of what can happen. Again, we can go back to this if you like. This is some old good Boeing work on cryoplanes using rocket fuel, that is liquid hydrogen, and it turns out to be a lot safer than Jet A is. And it's just like cars, where radical automotive fitness made the powertrain in our SUV 3 times smaller. So it turns out then you need 30-odd times less cumulative production volume to get to competitive cost. So I'll end with 3 things here. Here's a little petting zoo of new kinds of very clean and quiet aircraft. The 2 at the upper left and the 1 at the lower right burn fuel. They can burn pure SAF. The others are all electric. And to be sure, these are still targets promised to investors. They're not yet fully developed certified realities. Some specs and some dates will slip. But there are so many and so capable firms in this game, I think they're unlikely all to fail. These are only a third of the industry plans we analyzed. Those are a fraction of the total. There are still quite a few in stealth mode. So this is the one corner of a large bestiary. And if you look at the timing of how fast these things are planning to enter the market, it's pretty clear that it's going to far outrun most analysts' expectations. So I'll close with a challenging opportunity that I offered the industry in keynoting its 2019 ATAG conference in Montreal, and that addressed ICAO, both sponsored by Boeing, both very warmly received by Airbus and by the major suppliers. It's an implementation concept that a lot of them loved, and I think could help bring to fruition many of the technical ambitions I've described. For a decade, we have had the technology to create 3 to 5-fold more efficient airplanes if someone would make them and someone would buy them. Now there are even greater gains clearly in sight. Why should we take a century to do that incrementally when we can leapfrog straight to it? Well, because major airplane buyers, even if they have the capital, are understandably risk-averse. Airframe makers don't want to risk huge development investments for a radically better product that might not sell. So incrementalism prevails as we squander fuel, money, carbon budget, and precious time. The climate crisis will not wait. Business as usual won't work. Aviation's license to operate will erode, and our shareholders and voters and children will judge us negligent. So what if a powerful consortium of major customers, airlines, lessors, delivery and air logistics firms, military, relieved the airframe makers' market risk so they could fully focus their skill and ambition? The buyers could collectively solicit a super efficient airplane by publishing very demanding specifications, very clean, at least quadrupled efficiency, and then collectively commit to buy X copies a year for Y years at price Z from whoever first brings it to market, with a consolation prize for the runner-up. This would elicit and reward innovation for the airplanes that they're going to buy anyway. It unbundles buying airplanes from buying innovation. That changes the supplier's culture and brings out the best talent of their best innovators. That, I think, yields a very different product slate, reducing risk to both parties, most of all to the buyers. This method is called a golden carrot, sometimes called an advanced market offering or advanced market commitment. It's worked well for 35 years now, for over 20 diverse solicitations, from Sweden to France, from America to India, and it's time we seriously considered using it for airplanes. That could decouple flying from climate change, and unlike carbon offsets, it could also slash fuel costs and the risk of fuel price volatility. It could greatly increase energy security and national security, and it could unleash a huge burst of innovation that could transform aviation forever. What are we waiting for? Thanks.